I have one more equation to balance. Okay, I saved the best to last. So we're dealing with carbon, hydrogen, and oxygen. Carbon, hydrogen, oxygen. I'm going to go ahead and I'll pick purple. I'm going to go ahead and put squiggly marks here so I don't forget. Actually, I'm telling you, this is what I do sometimes with my answer keys. I put squiggly marks where I can put stoichiometric coefficients. That, I think, it drives you to know that you cannot change the subscripts, I hope. So what we have with coefficients of 1 across the board, how many carbons do we have? It looks like we have 4. How many hydrogens do we have on the reactant side? We have 10. That's a lot. How many oxygens on the reactant side? We have 2. On the product side, how many carbons do we have? I'm liking 1. How many hydrogens do we have? I'm liking 2. How many oxygens do we have over here to start out with? I'm liking we have 2 here and 1 here for a total of 3. Okay, so that's what we have to start out with coefficients of 1 across the board. Now, what is the only thing up there that's in its uncombined elemental form? So we'll leave it till last. The answer is this guy right here. We're going to leave the O2 till last. It's uncombined elemental form. So let's go ahead and focus on the carbons. So let's see. I have 4 over here. How do I get 4 carbons here? Well, if I put a stoichiometric coefficient of 4 in front of the CO2, then I have to update my carbons and my oxygens. So yep, that gave me 4 carbons, and how many oxygens do I now have? Don't forget the oxygen over here. So the number of oxygens I have is 4 times 2, 8, plus 1. I'm liking 9. I've got 9 oxygens. Very good. Now let's fix the hydrogens so as to speak. So I have 10 hydrogens over here. And how do I get 10 hydrogens right here? Well, if I put a 5, since they come in pairs, if I put a 5 here, that should give me 10 hydrogens, right? So now I have 10 hydrogens, and then how many oxygens do I have? Well, I have 5 oxygens brought by here, and what we say, 8 oxygens brought by here, so 5 plus 8, I'm liking 13. So let's see, what is not balanced? Well, the thing that's not balanced yet are our oxygens, okay? Now, we run into this with oxygen, especially if we kind of leave it to the end like this. Notice that I have kind of an even, they come in pairs, but the number that I need is an odd pair, is an odd number. So what I like to do is to say if I need, I'm going to go with halves. If I need 13, actually over here, do you buy this? That if I go with 13 halves O2s, do you buy this? This is my stoichiometric coefficient, and this is my formula. Does it seem like I will have 13 individual oxygen atoms? That is totally it. So when I say 13 halves of O2s, I mean 13 halves of this. Here's my O2 molecule. 13 halves. So you split it in half and you take 13 of those. Okay? So actually, one of the first answers, or one of the first ways to work this, I'm going to show you, is going to put a 13 halves in there. Update my O2s, and like I tried to convince you, now I have update my oxygens. Now 13 half O2s, I have 13 oxygens, which now balances with this. Okay? So, what do you think? So that's actually, you might be saying, well, I didn't think you could take, what I started to say is that's actually legitimate, but you didn't think you could have a fractional coefficient, and yes, you can. You can't have a fraction of a molecule, but I'm going to actually tell you here in a minute, if you think in terms of moles, you can have a fraction of a mole. So the next slide actually does something. This is what I call a recipe. So the recipe says, and we'll be talking more about this when we talk about stoichiometric calculation. Recipe takes 1 of these, 13 halves of these, 4 of these, and 5 of these. Or I should say it forms 4 of these and 5 of these. If you want to scale up a recipe, the thing that you make is like the product. What you do is basically take everything up or take everything down, a factor of something. Like you double everything, you halve everything, you triple everything. So actually I could take everything by 2. I could up it by 2. And if I did it by 2, then that actually now I would have what, 2? I would take 2 of these. Okay, what's 13 halves times 2? 13 halves times 2. What do you get? I get 13. So if I scale this 13 halves up by 2, I actually get 13. Oops, I should put this up here. This is my alternate set down here. I get 13. Okay, what if I take 4 times 2? I'm going to get 8 of these, and if I take 5 times 2, I'm going to get 10 of these. Okay, so what I've written down at the bottom, I know it's really messy, the stoichiometric coefficients of 2, 13, 8, and 10, that's like an alternate scale up of the original coefficients I had of 1, 13 halves, 4, and 5. Do you see how that works? Okay, so both of those are totally legitimate ways of balancing this equation. You can go through the process if you want, but this set of coefficients down here, this 2, 13, 8, and 10, which actually is double each of these, okay, we scaled it up, they balance the equation also. Same number of carbons, hydrogens, and oxygens on either side of the reaction arrow. And this matrix kind of talks you through what that looks like. Okay, so very good. This matrix talks you through the first way. So we'll be coming back to this idea of having those stoichiometric coefficients kind of scaled up from individual molecules and formula units to actually moles of the reactants and products. But you can definitely do a fractional stoichiometric coefficient. I'll tell you that the fractional stoichiometric coefficients work well when you have diatomic elements like O2. Like 1/2 O2 makes sense. You have like just 1 oxygen. So there is some limited to times you want to use fractional stoichiometric coefficients. So let's see what you think. Balance your own equations.